Okay, and now let's consider the principle of conditional error. First of all, for the computation of SSH, we can get a better formula apart from this PCE. I call it PCE here. For mutually orthogonal T's, we know that if Ti is independent of Tj, or better say, if they are mutually orthogonal, then we can conclude that Ti prime Tj is equal to 0, and I can find a very simple formula for SSH, which is given by this Ti prime y power 2 square, and then in the denominator Ti prime Ti. Okay, so you can sorry, it must be S here. So you can easily compute it under this assumption, but this is not always the case. But not always Ti prime Tj is equal to 0. So we need to take a better action for that. Remember, in general, we have the expected value of y equal to xp. Now we want to explain this principle of conditional error, which will give a simple formula for computing some square of hypothesis. Actually, we want to work with a reduced space or regression space, and then we will see reduced spaces for the error, and then for working with that reduced space for the error, everything will be solved. So we want to see how this reduction happens. Under the null hypothesis, under H0, H0, you have Q prime B equal to 0. So I can conclude that the expected value of y under this null hypothesis is equal to x naught b naught, or x0 b0. So here we have fewer parameters, we have fewer parameters, and here we have fewer observations, fewer design. In this case, the sum square of error is called the error of the reduced space. So it yields a new space, the space Vr minus S. In this space, the rank is equal to R minus S. And we can then decompose our space into two mutually orthogonal spaces. So we can construct or regression space. Let me use the pointer. We can construct our regression space as these two orthogonal spaces, the reduced one and this space which is obtained by the columns of S vectors. First of all, Vr minus S is orthogonal to Vs with a geographic representation, or better say in a schematic representation. I will show you how it works and how we can construct these two spaces. But let's see, how can we do that? How can we construct these spaces? First of all, a necessary and sufficient conditions must be satisfied. The expected value of T prime y must be equal to 0. The reduced regression space must be a subspace of the original regression space, and the rank of x0 or x0 must be equal to R minus S. The implication of this set of conditions, regularity conditions, is that then you can write V, the conditional error space, as the Vs, the composition of Vs and Ve. And furthermore, I can then construct the sum square of hypotheses as the sum square of conditional minus the sum square of error, or better say the SSR minus SSR under the null hypothesis. Now, in a schematic representation, we will explain these formulas in details, and you will understand this decomposition better in the schematic representation. It will also happen for the sets, so you can write the conditional error sets as the regression set of with S elements, orthogonal to the regression set of the set of errors. Now let's look at the schematic representation in order to understand it better. Let me minimize it a little bit to use different notations. Okay, in this schematic representation, first of all, we have this regression space. So this is, or let's consider VR as our regression space. You have the vector y, and you want to obtain the estimates in this space. We conduct a projection onto this VR, and the projection of y is xb hat, and the square length of xb hat will give you SSR, the sum of squares. Now consider the reduced estimated space. Let me use another color. This is actually the subspace of VR. How can I, geometrically construct a subspace? I will say, okay, I divide this space, and this with this line. With this line here, I can construct the subspace. So if I use also this color, no, not this one, it's too dark. Let's use this one. Yeah. So you see, this line actually shows the reduced space, and here we have. If I want to use the same color, so here we have the reduced estimator space. Reduced estimator space. And it's obtained under the null hypothesis, under Q prime B equal to 0. So it means that S of the functions are equal to 0. In this subspace, S of the functions are equal to 0 according to this linear combination of the parameters. We will say S of the parameters is equal to 0, and the rest of the parameters is actually R minus S. But what will happen about the projection of Y? If you project Y onto VRS, this subspace, then you will get X0 B hat 0. So this is the projection, and indeed in this case, this is the error. This is the error of this projection. So it is given by y minus x x0 b0, and the square length of this is sum of squares of conditional regression, or better say error. Sorry. The sum square of conditional error, and also consider, if I let me change it to blue. If I consider it as the projection of y onto VR, this here we have it as the error. So the square length of this error is actually sum square of error, which is SSE. So you can obtain SSE in this way. Here, now let's have a better look of what is happening here in this subspace. Now let's consider between the difference of two solutions. I use another color. So in one solution is here and one solution is here. So we have two solutions. Let's consider the difference between these two solutions. The difference between two solutions, I can write it as xb hat minus x0 b0 hat. And it is then the square length of this is actually sum square of hypothesis. So it is the difference between two solutions, and you can consider this is the difference between two solutions. Once again, if I highlight it, this is the difference between two solutions. And the square length, as I said, of this difference is the sum square of hypothesis. Now, in order to understand this decomposition, how can I understand this decomposition? It is very essential. According to this decomposition, you will easily get SSH. You can easily compute SSC, or better say SSR, and then if you subtract SSE out of that, you can get SSH. So you see, I have a shortcut in order to compute the SSH. But in order to have this shortcut, I must start from this equality. But how can I motivate or justify this equality? How can I write SSC based on SSE plus SSH? Now let's consider this construction. Let me use another one. Let's work with orange. Okay. Now, if I look at SSH, this is the SSH, and also SSE, the angle here, let me write it by orange color. The angle here is 90 degrees. So what does it mean? It means that if I sum SSC with SSH, so if I sum SSC plus SSH, I will get this one. I will get this one. And this one is nothing than SSE, in the original regression space. So you will see, you can write it. Sorry, I must write it SSH. So the summation of these two sum of squares is equal to summation of this sum square which obtained from this, the square length of this, and sum square which obtained from the square length of this. If I add these two, this is this angle. Okay, so I can write it as SSE. And then you will find that, okay, SSH is equal to SSC minus SSE. You can easily compute SSC. SSC, once again, remember from the green, from the green, let me use the pointer. From the green, if you compute y minus x naught b naught hat, the square length is equal to SSC. So you can compute SSC. You can easily compute SSE. It is y minus x b hat in the original space. And then you can easily get SSH. And in this way, we can then use the generalized F statistics in order to check this null hypothesis. I stop this video here, and in the next video I will go with the example to understand it better. Thank you.